Crane boom recoil as a result of sudden loss of load. I'm going to show a calculation by an energy balance method and also 2D dynamic simulations in Excel, and compare those with 3D dynamic simulations in Orcaflex. We're going to cover these issues in this slideshow, and you can come and replay the slideshow again anytime you want, but the main thing we're going to be focusing on here is the backward recoil calculation. Here's an example of a recent video I came across down in the BVI where a crane barge, or a barge and a crane, was having a problem. I'll replay that again because they were lifting a load with a crane on a barge, some rigging snaps, and the boom comes over backwards and lands down on one of the vessels they've just salvaged. A model test can tell you quite a lot. This is a model 12 scale. I've disconnected the boom stops. We'll play the simulation or the model test slightly slower than real time, and you see the boom springs back to vertical. We'll play it again. The boom can't pass vertical because of the plastic construction in the model. It would have done. We'll go on to the next slide. On to another test. Now this time the boom stops are properly connected. I had them disconnected in the last movie. And here when we drop the load, the boom stops compress. You see they compress quite a lot, and they end up at some slightly extended length, but the boom stops did actually stop that boom going vertical. Here we're looking at a comparison between the very quick analysis, practically instant, in Excel where the boom positions are shown, and what we get with an Orcaflex analysis with the same simple boom. We see the replay time clicking away here, and we see the positions over here with seconds, and we see that the times are virtually identical. Then we go on to the static solution and how it works. There's only a few values to input in the yellow cells. The basic geometry setup is shown on the right hand side, and a description is given. You can stop this slideshow anytime if you want to look more carefully at the slides. Now we compare Excel time history with the time history of Orcaflex for the first critical, in this case 0.22 seconds after the hook load is suddenly released. We see that in that first 0.22 seconds both Orcaflex and Excel predict the pendant tension will go to 0. During this time the boom is being accelerated, an angular acceleration caused by the sudden release of tension in the pendant. We can compare how the time history of the boom declination angle compares with the boom declination angle in Orcaflex. The time histories are nearly identical, and remember that the boom elevation angle we commonly talk about with cranes is 90 minus the declination angle. Now the boom recoil angle variation with different hook loads dropped, we can set up Excel to look at a range of hook loads with reasons behind these odd numbers, and we can see how the different hook load will result in a different angle of the boom after recoil, and we can compare an initial recoil starting at 80 degrees, so these light blue numbers, or the royal blue numbers 80 degrees but with thicker wires, and similarly starting at 70 degrees with the brown line, or the red with 70 degrees starting and thicker wires. So to recap on that previous slide, only one of the 4 calculation tables that create the data for the curves on the previous slide was shown. With 4 pendant wires, each 1.25 inch diameter, a sudden loss of hook load when the boom is at 80 degrees when the load is dropped will cause the boom to recoil back to vertical, depending on the load. With 4 pendant wires, each 1.5 inch diameter, the sudden loss of hook load, the same hook load, will only cause the boom to recoil to 84 degrees. So the magnitude of the hook load loss should be taken from the chart or the floating service chart if the crane is on a barge. So here's an example of a crane on a barge floating service chart, and the upper load chart values can be limited by boom recoil. So this happens to be for the Lima B or Lima 2400B crawler crane, and after bespoke derating for its floating service on this particular barge, the broken black line shows the upper load limits that were further imposed, limiting the upper loads it could carry because of boom recoil. Consideration of the trim angle, floating load service charts on the Comninos barge, 1.25 inch wires for the boom, and the particular load case that's shown down here is described in the next slide. It's a very small load, so it's a very small load, very close to the end of the barge, short radius, high boom angle, but note the crane doesn't have boom stops. The boom stops should be in this area. There are no boom stops. The NAA, the Naval Architectural Analysis Plan, for this load case contains, well, you can create this picture, so the boom is extended in this direction. A lot of information is given, but the maximum load that could be carried over the end is shown in the load case, and that includes the effect of lack of boom stops. Now, if we wanted to model force-in boom stops, if they were fitted and operational, the Orcaflex model can be set up to do that. A lot of information can be found. The model can be as detailed as the analyst wants. In this case, the force in the boom stops is predicted after, well, we saw in a previous slide the decay if no boom stops were there, and somewhere around 3 seconds we'd be reaching vertical, or 4 seconds. In this case, the boom stops kick in, push the boom back, and we see the boom takes the boom stops, then suddenly goes, well, slowly goes back and is jerked at this point by the tension in the pendant wires and springs back again. So that's the boom recoil from a sudden loss of load. Calculation of all these things are possible. You can replay this slide and replay this slideshow and look at all the values again.